Alright, so today we're talking about 13.3 in your textbook. And we've got two symbols that we want to talk about in 13.3 and what they mean. And the first one we're going to focus on is sigma. And sigma is a Greek letter, and we're going to use it to take the sum of a sequence or a series. So we'll usually see sigma and have it referred to as sigma notation or summation notation. So we've got sigma notation or summation notation. And the way we're going to write this out would be, for example, if we had, and we'll probably start with an arithmetic sequence, say we want to add up the first 20 integers. So, for example, instead of writing out 1 plus 2 plus 3 plus 4 plus all the way up to 20, we could shorten that a little bit and say that we want to take the sum from I equals 1 to 20 of I. And those two things would really mean the same thing. They're equivalent. So what we have to talk about here is with this sigma notation, we have a couple of values that showed up, like that I equals 1 and that 20. I equals 1 is what we refer to as an index or an indexing value. And what the index tells us is it gives us a location that we're interested in. So we're going to first be interested when I equals 1. And so I equals 1. And then the sigma says to take the sum or add to it. And then we let I go to the next integer. So now I becomes 2. So we're going to add the 2 on, and then we take the sum, which is what sigma stands for, and we let I go to the next number, which is 3. And we would do that all the way up until we got to that number on the top, and that number on the top, 20, tells us where to stop. So once I equals 20, we're going to stop what we're doing. So you can see that it really represents the same thing. We just have to pay attention to the value that we start at for I, and then the value that we end at for I. So let's look at an example here. And just to see what we want to do, we'll move on and we'll do a geometric series, which you guys looked at in the last section. So remember, for a geometric series, what we have is we're going to multiply by the same value every time. So let's say we want to take the sum of the first 5 terms of a geometric series. So we should probably write out the geometric series. So here we have a geometric series G, and we're going to let that be equal to 2, 6, 18, 54, 162, and we could go on from there, but we only need the first 5 because we're going to stop when I equals 5. So what this sum really means, if I take the sum from I equals 1 to 5 of G sub I, so that means that I want to take G sub 1, the first term in that sequence. I'm going to add it to G sub 2, the second term in that sequence. And we're going to continue on until we get all the way up to the 5th term. So again, starting at 1, G sub 1, ending at 5, so G sub 5. Now we can replace those with numbers because this index value of 1 means that we want G sub 1, or the first term of the sequence. And the first term of the sequence just happens to be 2. So I'm going to substitute 2 in there. The second term of the sequence is a 6, so I'm going to substitute in 6. The third term of the sequence is 18. The fourth term of the sequence is 54. And then last, the fifth term of that sequence is 162. So we're going to add these all together now, which is what the sum tells us to do. And if we add these all together, I'm actually going to pair the 6 with the 54, because I know that they add together nicely to make 60. And then I'm going to pair the 2 with the 18, because they paired nicely together to make 20. And then I've got that 162 that's still left there. And I see that 60 plus 20 is 80, plus 162 is 242. So that works rather nicely for that geometric sequence. And we were able to get the sum of the first 5 terms. Now, you guys saw last section that we learned a little bit different formula for this, and that last formula still applies. So if we look at it in terms of the last section, we want to take the sum from I equals 1 to 5 of G sub I. And in the last section, you guys might remember the formula, where that would mean that we have to take the first term, G sub 1, and multiply it by 1 minus R to the n, divided by 1 minus R. And what's nice is that that n value that we have here is exactly the same as the n value for the summation notation. Right? I mean, if you look in your textbook at summation notation, you have the sum from I equals what's usually 1 all the way to n. We have an n value of 5. And the R value that is written here, if you guys remember from the last section, is the number that we multiply by to move from one term to the next in our geometric sequence. So if you go back to find R, if you go back up here to these terms, you can see that from 2 to 6, we had to multiply by 3. From 6 to 18 by 3, 18 to 54 by 3. So we're timesing by 3 each time. So that becomes our R value. So we can rewrite this as G sub 1, the first term, which if we go back up is 2, times 1 minus the R value, which is 3, to n, which is 5, because we want the sum from 1 to 5. And then we're going to divide that by 1 minus that R value again, which is 3. Now, to simplify this up a little bit, 3 to the 5th is really the problem if we don't have a calculator. So we want to do 3 squared times 3 squared times 3. 3 squared times 3 squared is 9 times 9, or 81. And 81 times 3 is 243. So now we have 2 times 1 minus 243 over 1 minus 3. Or to clean that up a little bit more, 2 times negative 242 over negative 2. Now hopefully we can see that since it's multiplying on the top and then dividing by a single value, that these 2's will reduce out, and those 2 negatives cancel each other out and become a positive. So we get a final value of 242, which is luckily what we had up here. So both methods check out to be equivalent. So that's the summation notation. Again, just remember that when we're taking the sum of I equals 1 to n, that simply says that we have to have something, so let's say of I, that simply means that we want to take and add all the values until I becomes equal to n. Okay? And as we saw before, it doesn't always have to be an I there. We had G sub I, which meant that we want those terms of a sequence. We could have something completely different. Let's say we wanted to do a sum, for example, of some terms that we already had an explicit formula for. So maybe we want to do the sum from I equals 1 to 4, and maybe our formula is 3i squared plus 2. So what that would mean is, first thing I'm going to do is let I equal 1. And let's see if we can get rid of some of that glare. So if I let I equal 1, the first thing that we end up with is 3 times 1 squared plus 2. And then I want to add to that when I equals 2. So 3 times 2 squared plus 2. And then we're going to add to that when I equals 3. So 3 times 3 squared plus 2. And then last we're going to add to that when I equals 4. So 3 times 4 squared plus 2. So now I can go through and add up all those values. 1 squared is 1, times 3 is 3, plus 2 is 5. 2 squared is 4, times 3 is 12, plus 2 is 14. 3 squared is 9, times 3 is 27, plus 2 is 29. 4 squared is 16, times 3 is 48, plus 2 is 50. And now when we sum those all up, it looks like we have here 19 plus 29 is 48, plus 50 is 98. So again, the sum works the same way. We just have to put that index value of I in for whatever I is until we get to that number on the top. So notice that we had 4 things that we were summing together, and that is because I went from 1 to 4. So 4 distinct values there. So that's